All right, so we went over molecular formulas and empirical formulas on Friday, talking about these different compounds and how the molecular formula is just a basically an accounting of all your atoms, right? And you indicate the number of each atom with a subscript. So we talked about that. And then the empirical formula is like the reduced form of the molecular formula. But you need when you reduce it based on that law of multiple proportions, when you reduce it, it's got to be whole numbers, so it can't be fractions. So something like CO2, you can't reduce because this is understood to be a 1. And so that would be 1/2 if we divided everything by 2. So you want everything to be a whole number. So now let's get back into this part, number 8. Let's start at number 8. And it says for each of the following compounds, state whether it is ionic or covalent. And if it's ionic, write the symbols for the ions involved. So the basic rule of thumb here, we're going to need a periodic table. The rule of thumb here is that it's ionic if it's a metal and a non-metal. So if it's a metal and a non-metal, it's going to be ionic. If it's two non-metals, let me put the date up here, 214. It's covalent if it's two non-metals bonded together. And based on the periodic table, where are the non-metals located?
On the right side of the periodic table.
Anybody? Where are the non-metals located based on the periodic table?
Could you hear me?
No, I couldn't hear you.
Okay. On the right side of the periodic table.
The right side, and there is actually a demarcation line, right? There's a zigzag between the metalloids and the metals, and then the non-metals. So good. All right, so is potassium a metal or non-metal? Because that's let's look at A. So you got potassium, and then this thing right here is what we call a polyatomic. So we're going to approach these two different ways. We're going to do the crisscross method where we pull them apart and figure out what the charges are, and we're going to name it. All right. So this is a polyatomic. I sent you a list of polyatomics Friday, or at least a link to it. Did anybody pull that list up? And if you did, tell me what ClO4 is. It's on that list.
You sent it through email?
Yeah, I sent it in an announcement along with links to the videos and all that stuff. Okay. All right, let me pull it up. I'm gonna put it in the chat. Let me find where I saved it, and I'll put it in the chat right quick. Where's my okay? All right, let me upload this to the chat. If you're on your phone, you're not gonna be able to see it. But if you want to see it, you need to go to Blackboard and open and click the link that's in the announcement. All right, so there should be a PDF document of the table of polyatomics. Let me add it again because I was okay now. All right. So click on open that document up real quick, and we're gonna use that because that's a huge part of nomenclature, is knowing the polyatomics and what the names are.
Okay, I have a question.
Go right ahead.
I'm looking and I see ClO4. It's just a negative ion. I'm not sure
Mhm.
if that's the same.
Good.
Is that
Yeah.
right? Oh, okay.
Okay. I'm gonna show you why that looks like that in a second, but I want you to see it first, right? And if you look on the sheet, it's right under dihydrogen phosphate
Mm-hmm.
is ClO4 is an
Per.
ion perchlorate. So these polyatomics. Let me give you a definition for that. So a polyatomic is an ion composed of multiple atoms. Right. So ion composed of multiple atoms. Right. So if it's a polyatomic ion, that means that those atoms are grouped together in such a way that they have a charge. Right. So if we look at the ClO4, if we were to draw it out, we haven't done Lewis structures yet, but a ClO4 actually looks like this. So a Cl, it has a double bond to oxygen here, double bond to oxygen here, O, and then O. The chlorine has a +1 charge, and then the two oxygens, which all have lone pairs around them. You can write this down, by the way, because we are going to do Lewis structures soon, just not today. So that ion has an overall charge of, we're going to put it in brackets and say that it has an overall charge of -1 because both oxygens are negative and then the chlorine itself is positive. All right. So this is why we call it a polyatomic. It's actually a covalently bound molecule that has atoms in it that are covalently bound to one another. All right. But it has a charge of -1. And so when we look at this, the K is potassium. That's off the periodic table. That's a group 1 element. I'm going to cut this out, the next one out, so we can have room to expand it. And then we know that this is perchlorate. So the name of this compound would be potassium perchlorate. That's the name of that compound. The reason why it looks like it does is because, remember, I showed you this crisscross method. So potassium is group 1, so it's going to have a +1 charge. And then ClO4 is a polyatomic. All those atoms are together and there's negative. So when we crisscross these charges, and we're going to do more of these, so don't panic right now. When we crisscross them, there's going to be a 1 that comes because this is +1, this is -1, right? So when we crisscross the charges, it becomes KClO4, right? And the ones are understood to be here. And then if you want to put this in a bracket, you can. It's not necessary if a 1 is there, but there may be a time where it may be a group 2 element with this. And then it's there's a 2 there. If there's a subscript outside of that polyatomic, then you have to put it in a bracket. All right, let's do more. So let's take so is this compound ionic or is it covalent? The overall compound now, not the polyatomic. We don't care about that. We know that that's covalent. But when you bring that in the presence of potassium, then is it ionic or covalent? Because that is a non-metal, right? Chlorine and oxygen are both non-metals. Is that right? So we literally have a metal and potassium and a non-metal with the perchlorate anion. So this is ionic. Any questions about that?
Okay, wait.
Come
I
on.
think okay, so ionic and covalent. I mean, hold on, give me one sec. Non-metal and metal
It's
defines
ionic.
ionic. Mm-hmm. And
Mhm.
then for covalent, is it both non-metal and non-metal or
Yeah, so
metal?
two non-metals together, bonded together.
So just two nonmetals, not
Mhm.
vice versa.
Yeah, yeah. So if you have two nonmetals together, the 9 times out of 10 is going to be covalent. That
Okay.
one exception, I think I mentioned this. I don't know if I mentioned it to y'all or to the 1 o'clock class, but there's one exception with the covalent bonds involving a metal and a non-metal, and that's in a very, very specific case of what we call organometallics, where you have a metal with a covalent bond to a non-metal. But that's a very they're not to say that they're not abundant, because you can make them in the lab pretty easily, but that's a special case. So for the scope of this class, anytime we have a metal and a non-metal together, we're going to say that it's ionic. All right, let's do the next one. I'm gonna cut this out though, because I need more room to expand uh expand the work. So let me add a page. And I'm gonna cut all the rest of these out, and then we're gonna do each one by one in its own separate uh section, because this is a really important topic. Very important topic. If you can name, when you see the name, you can go from name to structure. If you see the structure, you can go from structure to name. That's the objective. I want you to be able to do both. Right? If I give you a name, I want you to be able to write out what that structure is. If I give you a structure, I want you to be able to write out the name. All right, so we'll paste that here. All that. But let's take magnesium right here. So this. So magnesium is a metal, and then the ion that's here, it's another polyatomic. It's on the list. Let's see if we can find it. Anybody found it yet on that list? Scroll down as far as you need to scroll down until you come to it. Look for those exact atoms: C2H3O2.
Acetate.
Acetate. Excellent. So this is the acetate anion, and then so you can kind of tell, and there's a subscript 2 out here. There's a reason for that. We're going to show you what the reason is, but you can tell that these are ionic because the polyatomics have a negative charge, many of them, and then the metal itself is going to have a positive charge. So this is magnesium. So it's a metal, and this is a non-metal. So that's a metal and a non-metal. So this is ionic, right? Because there's a attraction between a metal and a non-metal. Also, let's think about this in terms of why there's a subscript 2 down here. There's a reason for that, right? And also what the acetate anion is. So let me show you what that looks like. So you see on the sheet where it says CH3COO minus. So the acetate anion actually looks like this. So there's a carbon, it has a double bond to oxygen. It has a O, another oxygen bonded to it, that's negative. And then this is CH3. So this is the acetate anion. This comes from acetic acid, which is what the principal component is in vinegar. So this is the acetate ion. You can see it's -1 because the formal charge on oxygen is -1. So the overall charge is -1, right? Can somebody, anybody remember when we talked about formal charge? How did we calculate that? I gave you a very simple way to do that. Anybody remember? Right, I said if you take the valence electrons and subtract it from the actual electrons, that's the formal charge, right? So what group is oxygen in on the periodic table? Go all the way across, past the metals into the non-metals. Tell me where oxygen is.
Group 6.
Group 6. So oxygen has 6 valence electrons. That's what that means. And then when we say actual, what we're going to do is count the electrons around it here. So this is 2, 4, 6. And then this bond right here is actually composed of 2 electrons. So we're going to take one of those electrons from that bond. So right now in that molecule, oxygen has 7 electrons around it. So 7 actual for a charge of -1. All right. Any questions about that before we move on?
Why isn't it 8?
When you're calculating formal charge, you just split. So any bonds you have between atoms, you just half the number of electrons. So every bond is composed of, let me draw this out. If I drew this as a sigma bond between these two, there are 2 electrons in here.
Right. Instead
So
of
one of
just-
those is, so covalent means shared. So that those electrons are shared between those 2 atoms. So
Mhm.
oxygen is holding on to one. Well, it's actually holding on to both of them because it's more electronegative, but we didn't talk about that yet. So it's pulling those electrons towards itself, but when you're counting them up, you only take one because it's a shared pair of electrons.
Okay.
All right, we're going to talk a lot more about formal charge. I just like to touch stuff when it's there, just to keep it fresh in your mind. So when you see it and we actually start studying it, it's like second nature at that point. All right, so so this is the acetate anion. So why does this have this formula, molecular formula, Mg, and then the acetate has a subscript 2, right? What group is magnesium in on the periodic table?
Alkaline earth metals.
Which is group what? What number?
2.
Group 2. So what charge would you expect magnesium to have as a metal? All metals are going to be cations, positive. Well, let me not say all. 99% of metals are going to be cations. There are some cases where you can have a metal with a negative charge, but it's very specific. But 99% of the time, your metals are going to be cations. If it's in group 2, that means it can have a charge of +2, or will have a charge of +2. So if we think about this magnesium, if we pull these 2 apart, the magnesium would be here as +2, and then the acetate will be here, C2H3O2 with a -1 charge. That's how we get that subscript, because when we crisscross these, right, this is going here, and then this is coming here. No charges, just values, right? So the magnesium is going to have a 1 here, which is understood. That's why we don't write it. And then the acetate, because of the charge on magnesium, it takes 2 of those to neutralize the magnesium, which is +2. Does that make sense? That's why. So if it's a -1 and this is the metal is +2, when you crisscross it, the subscript is always going to be 2. because that means that it takes two of those to neutralize that +2 charge. All right, so the name of this compound is magnesium acetate. All right, any questions about that? Right, if you notice, there's a pattern. The charges are going to cancel each other out. That's why when we do the crisscross, that's why those subscripts show up, because you're trying to, the charges are canceling each other. So if you have a metal with a +2 charge, you need either an ion with a -2 charge or two of those ions with -1 charges, if that makes sense. All right, so everything is trying to cancel and be neutral. All right, let's do another one. Let's do C. So it's H2 H2S. Is hydrogen a metal or non-metal?
A non-metal.
Non-metal, good. And then sulfur is also a non-metal. All right. So you think this is ionic or covalent?
Covalent.
Covalent. It actually looks like this, where you have sulfur with a bond to hydrogen on each side. This is actually a water analog. This is like water is H2O, H2S is like a sulfur analog of water. It's not drinkable, but it has the same structure as water. So this would be, you have two hydrogens. So we're going to use the Greek prefix di, not bi. Dihydrogen. Because I have two hydrogens, I'm going to use this prefix. So that's going to tell me the number of that atom. So since there are two hydrogens, I'm going to call it dihydrogen. And then for sulfur, anytime you have an element like sulfur or oxygen or carbon or chlorine or fluorine, you're going to change the suffix. So this would be dihydrogen sulfide. That IDE is indicative of the fact that sulfur is the, well, come on, Russell. I'm saying anion, even though it's not covalent. I mean, it's not ionic. That sulfur, since it's in group 6, it's going to be just like oxygen. It's going to be capable of forming a charge of -2, right? So the hydrogen has one valence electron, or it can be H+, right? So when you have a molecule like this, you name it based on, you put the hydrogen first, so it's dihydrogen, and then you put the central atom last, so it's dihydrogen sulfide. All right, questions about that? There are other like ways to name these covalent compounds, and the names depend on what type of compound it is. All right, so this is, since this is like this will be considered an acid. So we name it this way. We haven't talked about acids and bases yet. We're going to get to that. All right, any questions? All right, let's do D. What do you think? D has what is the symbol Ag? What is that on the periodic table?
You said what's the symbol H?
Ag.
AG.
Mm-hmm.
One second.
Look in the middle. Over to the right. Close to the metalloids. Top row, transition metal.
LMAO, I see it. I just gotta remember the name because the thingy isn't up there.
It
I'm
is.
serious.
Go ahead.
I was gonna get it confused with gold. It's silver.
It's silver. Gold is AU.
Right.
Silver is AG. And that's again, that's common, but that's why I said you may not have to memorize the periodic table per se, but there are certain elements you should definitely know. Like silver is one of them. Silver, gold, copper, nickel, cobalt, elements like that. And then of course the non-metals and metals, you should know those by heart. The transition metals, there's a lot of them, and we'll see them when we get to them. But definitely the group 1, group 2, and then group 3 through 7, you should know those. All right, so we got Ag2S. So silver is a transition metal. Excuse me. It's a transition metal. All right. And then sulfur, we know is a non-metal. Is that right? So let's see if you've been paying attention. Somebody tell me, not the name. Tell me if this is ionic or covalent, and then show me the two pieces, how you would pull this apart to see what the charges are on each piece.
Ionic.
Okay, it is ionic. It's a metal and a non-metal together. All right, if I were to pull these apart, so if I pull the silver this way and I pull the sulfur this way, what happens down here is these numbers are gonna go like this. So this is gonna go here, and this is gonna go here with sulfur. So what's the charge on silver?
All right, now I'm no chemistry whiz, but
Yes, you are. Yes, you are.
I'm not.
Yes, you
But
are. Don't talk yourself out of it.
we have to calculate, I think, the formal charge, which is
No formal charge right here. We don't even have any electrons showing. All we're doing, you see those subscripts? When we put, if you would like think about it like if you had two Lego blocks in your hand that were connected. If you pull them apart, the charges, so the charge down here is going to leave with the atom on the right. So it's going to leave with sulfur. And the number here is going to leave with the atom on the left. So I'm going to write this like this. So we know that all metals are cations. So I'm going to write this like this, +1. And then the sulfur, since the 2 is here, and we know that the metal is a cation, this charge has to be by default negative. So this is, when you have an ionic compound, you're going to always have a cation and an anion, right? So when I break these apart, the subscripts leave with the atom to the right of it, right? So, this is subscript here. The 2 is going to leave with sulfur. And then to the left of the subscript 1 is silver. So that's going to leave with silver. So that's how I know what the charges are. And then when I bring them together and crisscross them, the numbers go right back where they were. Right, so it's Ag2S. So tell me this, why do you need 2 silvers for every 1 sulfur?
because it only has a plus one charge.
One, exactly. And what's the charge on sulfur?
-2.
So you got to balance it out. That's the whole purpose. So it's, everything is going to be neutral, right? That's the goal. So this is silver. And what about sulfur? How do I name that since it's the anion? What's the suffix I'm going to use?
Sulfide.
Sulfide. That IDE indicates that this is an anion. That suffix. And you'll find out for your halogens and all those other atoms over there, it'll be the same thing. All right, let's go. Let's do another one. Let me see. Oh, this is a good one. This is a good one. All right, let's do E. It is N2Cl4. N2Cl4. So the fact that both of these are these metals or non-metals? Is nitrogen a metal or non-metal? If you find the metalloids on the periodic table, anything to the right of those metalloids is a non-metal.
What was the question? I'm sorry.
Is nitrogen a metal or non-metal?
Nitrogen is, I don't know, because that metalloid line is somewhere right here. Is it a non-metal?
Yeah, it's next to carbon, right?
Right.
And carbon is next to boron, which is the first metalloid. So anything to the right of boron is going to be a non-metal.
Got you.
So both of these are non-metal. So this would be covalent. All right. Now we have, let's name it, and then we're going to talk about the structure. So we have 2 nitrogens and 4 chlorines. All right. So with a covalent compound like this, you're going to use suffixes or prefixes to indicate how many of each atom is present. So since there are 2 nitrogens, what's the suffix for 2? We just used it. So di, I'm sure this is redundant, tri. 2 T's and tetra, come on, Russell.
Per is 4, right?
Tetra, no, tetra. Yeah,
Hmm.
so we're gonna use the Greek prefixes here for these for the non-metal. So di, tri, tetra, penta, hexa, like that. So this is what? Di, nitrogen, right? The di means that there are 2. And then tetra, what? Is it going to be tetrachlorine or tetrachloride?
Tetrachloride.
Yes, di-nitrogen tetrachloride. The tetra means that there are 4 chlorines. The di means that there are 2 nitrogens. So it's di-nitrogen tetrachloride. So tetra is 4. Penta is 5. Hexa is 6, so on and so on. And hepta is 7. So we're going to use Greek prefixes. For covalent compounds, right? That's not necessary when you have ionic compounds. So this wouldn't be disilver sulfide, it's just silver sulfide. But when you have covalent compounds, you want to use those Greek prefixes. All right, let's do this last one up here. Oh, it's a good one too. All right, look on the on that list of polyatomics and tell me what the polyatomic NO3 is.
Nitrate.
Nitrate. Good. All right, so we got another convention that we're going to discuss right here. Right? Because cobalt can be +1 or +2. All right. Now, how do we know which one it is? We need to know what the charge is on the nitrate and what the charge is on cobalt. Well, and the way we can tell that is from this formula right here, right? What's the charge on the cobalt if we pull this apart into its two constituents? So we pull it apart. Where's the subscript going to go? That's here. And then the understood 1, where does that go?
It goes to nitrate. The 1 goes to nitrate, and the 2 goes to cobalt.
Great. So this would be, and we know the metal is going to be the cation. So this is cobalt +2, and then NO3. The whole thing is a -1. All right, and the structure for NO3 looks like this. It is so this is negative. That's negative, and then the nitrogen itself is positive. So the overall charge is -1 because the 2 oxygens add up to -2, and then the nitrogen has a +1, so the overall charge is -1. Right? So the fact that cobalt can exist in 2 different oxidation states, we have to indicate that. Right? So when we write the name of this, right, we know that the oxidation state or the charge on, sorry, wrong pen. The charge on cobalt, we can also call this is oxidation state. The charge is +2. So we know that cobalt this particular form of cobalt is in a +2 oxidation state. So when we name it, we have to indicate that. So this is cobalt. And then to indicate we'll put a parentheses here. We'll put a Roman numeral 2, cobalt 2 nitrate. Right, so the cobalt is the metal. It is the Roman numeral 2 says that it's in the 2+ oxidation state. And then the nitrate, we knew the name of that from the list of polyatomics. So when we write this, we have to write it with that convention. So cobalt, if a metal has more than 1 oxidation state, we have to indicate it. And we can tell what the oxidation state of the metal is if we know the charge of the polyatomic that is ionically attracted to. Are y'all following that? So we know NO3 is -1. And we see a subscript 2 down here beside it. We know when we pull those 2 pieces apart, the 2 is going with cobalt and the 1 is going with the nitrate, right? If it was cobalt 1 nitrate, it would look like this, right? So cobalt 1 nitrate would look like that, right? Where cobalt here is CO, The nitrate is here. So this will be, we write this like this, cobalt 1 nitrate. Right? Anybody not following that or not catching it? It's all right, Saxon, we good. All right. Any questions? All right, we're gonna keep trucking with this. We got, bring this handout back because the rest of the questions on here are all nomenclature. So we're gonna keep naming these. Yeah, these are gonna be good right here. Make sure you're looking over those polyatomics and make sure that you are just taking a peek at your periodic table, like for a couple of minutes a day. So those elements will start sticking in your mind. All right, any questions about anything?